The topic of this video is how to simplify radicals. We're going to talk about principal and negative square roots today. For example, if a is a non-negative number, then that means the square root of a is the principal or the non-negative square root of a. When you notice the negative sign out in front of the root symbol, it's read as the negative square root of a. So to break this down, the symbol itself is called the radical sign. The term under the radical sign is the radicand. And sometimes we see a number written outside of the radical sign, and that refers to the index or the root. When you don't see a number written at all, the assumption is we are looking for the square root of the base a. The whole term is called a radical expression. We're going to start with the product rule for simplifying square roots. If a and b are non-negative, the square root of the product a times b is equal to the product of the square roots of a and b. In other words, if you have bases underneath the radical sign that are being multiplied, the product rule allows for us to separate those factors and place them under their own radical signs. So the steps to simplify are to factor any perfect squares from the radicand. In other words, by separating these factors of a and b, we really are hoping that either a is a perfect square or b is a perfect square. Of course, if they both are, that's fine. But if at least one of them is a perfect square, that is what allows us to simplify the radical expression. So we will write radical expressions as the product of radical expressions, and then simplify if there are any perfect squares. In our first example, we have the square root of 9. Well, you might already know that 9 is a perfect square. So if we use the product rule to show that, we could break down the square root of 9 as the square root of 3 times 3, which some people like to write as the square root of the quantity of 3 squared. In this notation, then it's easy to see that you have a perfect square under the radical and you're taking the square root, so they undo. They are opposite operations. Therefore, the base that remains is the base that clears the radical. So your final answer would be 3. With example 2, we have the square root of 49x squared. So another way that this could be written using our product rule is separating the numerical coefficient from the variable base. 49 you could think of as the quantity of 7 squared, and x squared is the quantity of x being squared. So then you can see that square root and squaring are opposite operations, therefore 7 would clear the first radical, and then the square root of a perfect square means x also clears the radical. So our final answer here is 7x. So basically what we're able to do here is convert from one notation to the other. We're starting with radical notation, and then we're able to simplify. So in order to check the answer, you could perform the opposite operation. So in the beginning, we are square rooting, so the opposite of square root is to raise to the power of 2. That means I could take the quantity of 7x and square it. By doing that, I have 7 times 7 times x times x. 7 times 7 is 49, x times x is x squared, and 49x squared was the original radicand. So you can see how it's fairly simple to check your work. In example 3, we have square root of 16. You might recognize that as the square root of 4 quantity squared. So to undo the squaring with square root, we end up with 4. In example 4, now we've got a negative. Since the negative is outside of the radical, we read this as the negative square root of 144. So the negative sign on the outside is actually indicating multiplication of negative 1. So negative 1 is multiplied by the square root of the quantity 12 squared, because we know that 144 is a perfect square. So the terms that clear the radical, negative is already clearing, and now we can see that 12 squared, taking square root, leaves 12. So negative 12 is the negative square root of 144. With example 5, we have 25x squared. So if you like to think of 25 as 5 times 5, you can see that is a quantity of 5 that's being squared under the radical. And we also have x squared. That's also a perfect square. So the terms that clear the radical would be 5 and x. That would be 5x.